In the previous lecture, we were discussing about synchronous sequential circuits. We looked at how using the same clock for all the flip-flops in a given circuit, we can use that to get some counting sequence that we would like. So I was mentioning towards the end of that lecture that it is indeed possible for us to use this concept to get any arbitrary count that we want. So let's take an example of a 3-bit. So let's say we want to generate a sequence which looks something like this. This is the counting sequence. Again, after this we have 2, 5, 3 and so on. So over here you need to look at what is the highest number that is being generated. So the highest number which we can see being generated is 7. So 7 in binary is 111. So that means once again we need a 3-bit counter or 3 flip-flops. So therefore, if this count is represented using the variables Q2, Q1 and Q0, we can make a state table which looks like this. So if the present state is 0, we see that 0 is not a part of the counting sequence. Therefore, the next state can be assigned as a don't care, based on our knowledge of using don't cares to make the circuit less complex in terms of additional gates. Now, if the present state is 1, we see that 1 is not a part of the counting sequence. So once again we will place this as don't cares. When the present state is 2, the next state has to be 5. When the present state is 3, the next state has to be 6. When the present state is 4, the next state has to be 2. 5 means the next state has to be 3. When the present input is 6, the next state has to be 7. And for 7, the next state has to be 4. So this is what the state table would look like. So now if I were to realize this using T flip-flops, for example, we would need 3 such flip-flops, and using the excitation table of the T flip-flop, let us try to fill in these columns just like how we did in the previous lecture. So for T2, we have to look at Q2 and Q2 plus. So these two would be don't cares. Zero and 1 would be a 1, again 1, again 1, 1, 0 and 0. For T1, look at Q1 and Q1 plus. These two would be don't cares. Then here we would get a 1, then 0, then 1, 1, 0 and 1. For T0, we have to look at Q0 and Q0 plus. These two would be don't cares like its predecessors. This would be 1, 1, 0, 0, 1 and 1. Alright. So using this we can make the Kmaps for T2, T1 and T0, each of them, and see what would be the expression for each of these. So let's first note down the minterms. So for all of these, 0 and 1 are don't cares. For T2, the minterms are 2, 3, 4 and 5. For T1, the minterms are 2, 4, 5 and 7. And for T0, the minterms are 2, 3, 6 and 7. So let's say for T2, let's construct the Kmap. Zero and 1 are don't cares, and the rest of the minterms are at 2, 3, 4 and 5. So therefore we can make a group of 4 this way. We can make another group of 4 this way around the edge. So that means T2 is equal to Q2 bar plus Q1 bar. For T1, once again we'll construct the Kmap. These two are don't cares. And the minterms are 2, 4, 5 and 7. So we can make one group this way and another group this way and another group this way. So we see that T1, for this group it would be equal to Q1 bar plus Q2 Q0 plus Q2 bar Q0 bar. This is what is T1. And for T0, the minterms are 2, 3, 6 and 7. So what we can do here, we can immediately make a group of these 4. These don't cares don't need to be grouped. So I can say T0 is equal to Q1. T0 is equal to Q1. So with this we can now draw the circuit. Let me now draw them in a vertical sense because it might be a little easier to grasp. So T0 is equal to Q1. So I can just simply connect Q1 over here and show. T1 is equal to a big expression, that is Q1 bar plus Q2 Q0 plus Q2 bar Q0 bar. So we will need an OR gate. So Q1 bar would come this way. So the next term we have is Q2 Q0 and Q2 bar Q0 bar, which will essentially form something like an XNOR operation. So we can show that XNOR gate itself. So over here it will be Q2 and Q0 I'm showing the whole diagram just so that you can get a feel of what such kind of logic circuits look like in practice. And T2 is Q2 bar plus Q1 bar. So Q2 bar plus Q1 bar is like saying it is Q2 Q1 whole bar. So it's kind of like using a NAND gate. So Q2 is already over here. And Q1, we can bring it, sorry, Q1 is over here, so not this one. We can bring it from here. This is what it would be. Finally, it is very important to show the clock. It can be positive edge triggered or negative edge triggered. Hardly matters. And obviously the outputs are these three. This is the MSB and this is the LSB. This is what this arbitrary counting sequence circuit would look like. So now if you recall, we had assigned don't cares as the next states for 0 and 1. So it is our responsibility to see if the present state is 0 and 1, what will happen to the next state. The counting sequence that we we're trying to do is this one. This is the sequence. So what is unused is 0 and 1. So what we essentially got, so suppose if Q2, Q1 and Q0, it is 0, 0, 0, that is if the present state is 0, then what will be the next states? So T2 is Q2 bar plus Q1 bar T1 is Q1 bar plus Q2 Q0 plus Q2 bar Q0 bar. And T0 is Q1. So therefore, if this is 0, 0, 0, T2 will be what? Q2 bar plus Q1 bar. That means T2 will be 1. T1 will be Q1 bar, that is 1 plus something, so it will always be 1. And T0 is Q1, which will be 0. So therefore, Q2 plus will be the opposite of Q2, that is 1. Q1 plus will be the opposite of Q1, that is 1. And Q0 plus will be the same as Q0 because T0 is 0, that is 0. So therefore what we get, the next state is 6. So if the present state somehow becomes 0, the next state would be 6. What about 1? What about 1? So if Q2, Q1, Q0 is 1, then let's calculate this. So T2 in this case will be what? Q2 bar plus Q1 bar, which will be 1. T1 will be Q1 bar plus something, which is again 1. And T0 is Q1, which will be 0. So that means Q2 plus will be the opposite of Q2, which is 1. Then Q1 plus will be the opposite of Q1, that will also be 1. And Q0 plus will be the same as Q0, which is 1. So here 1, 1, 1 means the next state is 7. So if the present state is somehow 1, the next state goes to 7. So the unused states or the undesired states are essentially coming back to the main chain that is desired. The main chain which consists of arbitrary counts. So as you know, these circuits which we have been looking at over the last few lectures, which involve these flip-flops, these circuits are called as sequential circuits. So in In general, what we have seen so far is that sequential circuits can consist of multiple flip-flops and some additional gates, especially if they are synchronous. So suppose we take a look at a synchronous circuit. You can have one flip-flop. It could be any kind of flip-flop that we know. Let's say there are two flip-flops. So to the inputs of these, there could be some combinational logic circuits. Similarly over here also. Now, these are the inputs to the flip-flops. Now, what is the input to the combinational circuit? We see that there are some state variables. So, let's say this is Q0. Let's call this flip-flop 0 and flip-flop 1. Let's call this as Q1 and Q1 bar. Sorry, Q0 bar. So the inputs to these will be Q0, Q1 and so on. It could be anything. And we saw that the outputs of the flip-flop so far are just the state variables. But in general, synchronous circuits, or for that matter any sequential logic circuit which looks like this, of course I forgot to show the clock. This same clock is over here also. So it's not always that the combinational inputs for the flip-flops would look just like this. That is, they will have inputs only as the state variables and the outputs will only be the states. Not necessary. You can have additional user inputs also, and the outputs can be some function of the state variables. So let us take a look at such a circuit which can be designed. Let us make a problem with this. So design a synchronous circuit such that it has a user input. Let's call this as some M. Let's call this as M. Now what does M do? If M is equal to 0, then the counter, or rather I should say the state, should increment by 1 at every clock. Let's call this as positive clock. And if M equals 0, then the state should increment by 2 at every positive clock edge. All right. Next, it has an output. Let's call this as Y. Now Y will be equal to 1 if the state value is divisible by 3 and the maximum count or the maximum state value of the circuit should be 15. Okay, so this is the specifications which are given to us. So if the maximum state value of the circuit is 15, in binary that is 1 1 1 1. That means we need 4 flip-flops. 4 flip-flops. Now what kind of flip-flop do you want to use? For this time, let us use D flip-flops. Let's use D flip-flops. Now what we are noticing is that it has a user input M whose value governs whether the counter state will add by +1 or +2. And or let us make things a little simple. Let us say that the maximum state value can be 7, because if we have 15, it might get a little bit too complex. So that means it is 1 1 1. So we will need 3 flip-flops. So we will be using 3 D flip-flops. So let us now draw a table. So let us say let's draw the table in decimal. So the present state, it can go from 0 1 2 3 4 5 6 and 7. So if the next state, so if m is equal to 0, then the next state will be 1. But for 0, if m equal to 1, then the next state has to be 2. So like this we are going to fill up our table. So what we are going to do is something like this. Let's call this as Q2, Q1 and Q0. Now I need to specify what is M, because that will tell me what is the next state. That is Q2 plus, Q1 plus and Q0 plus. So when the present state is 0 0 0 and the M is 0, the next state will be 0 0 1. That is plus 1 from the present state. Now when the present state is 0 0 0 but M is 1, this has to be 0 1 0. Then we have 0 0 1 0 0 1. When M can be 0 or 1, so over here it will be 0 1 0, it will be 0 1 1. Then we have, so this will essentially show that Q2, Q1, Q0 and M would essentially form kind of like 4 variables of a truth table. So let us fill it that way. So this would be 0, 1, 1 and 1, 0, 0. 3, when it is 0, the next state will be 4, else it will be 5. Again 5 and 6. 6 and 7. So now when the present state is 6 and the m is 1, so 6 needs to increment by 2. Now what is 6 plus 2? It is 8. That is not possible, because we know that the maximum count can only be 7. So therefore, if the present count is 6, plus 1 will make it 7, another plus 1 will make it 0. So therefore, this state will be 0. Similarly, if there is 7 and m is 0, 7 plus 1 would again make the next state 0, because that is how counting works. But if the present state is 7 and m is 1, we need to increment by 2. So therefore 7, 0 and 1. So it will be 0, 0, 1. Okay. So now we will have 3 D flip-flops whose inputs will be D2, D1 and D0. So from the excitation table of the D flip-flop, the excitation table looks something like this. So D is essentially the same as Q plus, so that is 0, 1, 0, 1. So all we need to do is look at this column of Q2 plus 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0. D1 will be 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. D0 is 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. Yeah, it will be here rather. And 1, 1, 0, 0, 1. So this makes this truth table complete. So therefore, let us try to find out what D2, D1 and D0 will be. So let's write the midterms first. So for D0, let's write for D2. The midterms are 5, 6, 7, 8, 9, 10, 11, 12. 5 to 12. D1, the midterms are 1, 2, 3, 4, 1, 2, 4 and 9, 10, 11, 12. And D0, the midterms are 1, 3, 4, 1, 3, 4, 7, 8, 11, 12 and 50. So let's construct the Kmap for D2. There will be a 4 variable Kmap: Q2, Q1, Q0 and M. So for D2, the midterms are from 5 to 12, 5, 6, 7, 8, 9, 10, 11 and 12. These are the ones. So we can make two groups of 2 over here, one group of 4 and another group of 2. So over here D2 will be now Q2 Q1 bar plus Q2 Q0 bar M bar plus Q2 bar Q1 M plus Q2 bar Q1 Q0. This is what it will be. For D1, the midterms are from 1 to 4 and 9 to 12. Something of this kind. So now the grouping can be made this way. One group like this, another group like this, and the third group will be these two. So we can say B1 is equal to Q1 Q0 bar M bar plus this will be Q1 bar M plus Q1 bar Q0. For D2, for D0, there will be one more Kmap. So where the midterms are 1, 3, 4, 7, 8, 1, 3, 4, 7, 8 11, 12 and 15. This is what it is. So we can quickly make one group of 4 over here, one group of 2 and 2 groups of 2. This we can make. So from here we can get D0 is equal to Q0M plus Q2 bar Q1 bar M plus Q1 Q0 bar M bar plus Q2 Q0 bar M bar. So you've got the different expressions for D2, D1 and D0. Notice that now they are not just functions of the Q states but also functions of M. So therefore the D inputs can be functions of the user input M also. But let us not forget that there is one more output called Y. There is one more output called Y whose function is defined that Y will be 1 if the state value is divisible by 3. So therefore the Y value depends only on the state. The Y value depends only on the state. So if I have Q2, Q1, Q0 and 1. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So Y will be 1. Let us say for 0, it will be 1. Next for 3, it will be 1. Then for 6, it will be 1. So this is just like a combinational circuit where Y depends only on the state and nothing else. So So 0 is a min-term, 3 and 6. These are the min-terms. So as you can see, there is no easy way to solve for it. So Y will just have to be written in the canonical subform, that is Q2 bar, Q1 bar, Q0 bar plus Q1, Q2 bar, Q1, Q0 plus Q2, Q1, Q0 bar. So what we can see now is that in this case, while the D variables were functions of the state and M, the output is a function of only the state. So therefore this kind of circuit where the output or given output or outputs of the system depends only on the state is called as a Moore circuit. Of course, there can be circuits where Y depends not just on the state but with the user input like M also. So those are called as Mealy circuits. In this particular example, we saw what is a Moore circuit. But in general, you may come across circuits which are Mealy also. So these are essentially two different kinds of synchronous sequential circuits, that is Mealy and Moore. So in this particular lecture, we discussed about first an arbitrary counting sequence, how that can be designed using T flip-flops, and after that we took a look at a generalized design of a synchronous sequential circuit where there could be additional inputs and additional outputs also, apart from the flip-flop inputs and the state outputs. So in general, those kinds of circuits can be of two types. One is the Moore type, the other is the Mealy type. Thank you.